Hey friends, welcome back to my channel. This is Aaheli and today we will study a super important topic, real numbers and their theorems. Now I know theorems can sound scary, but don't worry. I'm here to explain every single line in simple language, just like we are studying together, right? We will read exactly what was written in this book, SK Mapa, and then I'll explain it in simple language, okay? So these are the topics which we need to understand for today's class. Natural numbers are not bounded above. Between any two real numbers, there exists a rational number. Interesting. Between any two real numbers, there exists an irrational number. Very interesting. And then rational numbers are not complete. Okay. And the last one is Archimedean property of real numbers. All right. Now let's start with today's class with the first theorem. The book statement is let n be the set. What is the set of natural numbers? This is the notation for natural numbers, right? Yes. So how will we represent it? It is like this. And so on. And n is not bounded above. What does it mean? It means, is there some number bigger than every number in the set? This theorem says no. There is no real number that is bigger than all natural numbers. You're getting my point? This is what the statement says. Now we'll come to the proof. Okay. The first line is, let us suppose that, what do we suppose? Let's say n is bounded above. Like, let's assume the opposite, that there is a number, let's call it alpha, which is greater than or equal to every natural number. We consider alpha, which is greater than or equal to every natural number. Okay. Now for the next line. By the axiom of supremum. Now, I'll just take a moment to say, if you have not watched the previous video on supremum, infimum, and all the properties of real numbers, please watch it because this is important for today's class. Okay. Now let's continue with this. By the axiom of supremum, n has a supremum. We just now discussed about it, which is alpha, and it belongs to real number. All right. Now let me explain this. If a set is bounded above, it has least upper bound. It has a least upper bound. And what is this least upper bound? This is only supremum. Just a quick recap. Okay. Now comes the next part. Let m be a natural number such that m is greater than alpha minus 1. This is possible. How is this possible? Because we have already considered that alpha is the least upper bound. So how is this possible? This is possible due to the Archimedean property. Again, the previous video, referring to it, the previous video. Please watch it. What is the Archimedean property? Archimedean property says that we can find a natural number greater than any real number, right? We can find a natural number greater than any real number. This is what Archimedean property says. So by the Archimedean property, we can prove this statement. Now coming to the next one. M is greater than alpha minus 1, which implies m plus 1 is greater than alpha, which again implies m is greater than alpha, which is a contradiction, right? This is contradiction. Because we assumed that alpha is the least upper bound, but now we get is m is greater than alpha. Now, if I explain it, let's say m plus 1 belongs to n, right? But m plus 1 is greater than alpha, which contradicts the concept that alpha is an upper bound. All right. We found a natural number greater than alpha, but we assumed alpha is bigger than all natural numbers. Hence, our last statement for this proof is, hence, n is not bounded above. All right. Is the proof clear? Then coming to our next theorem. Do you remember what is the next theorem? The next theorem is, between any two real numbers, there exists a rational number. We will first write the statement, let A and B belong to R real number with A is less than B. Then there exists R which belongs to rational number such that A is lesser than R and R is lesser than B. What is the meaning of it? The meaning is you can always find a fraction or a rational number between any two real number. Between any two real number. So now we are coming to the proof part. Since B minus A is greater than 0 by the Archimedean property, there exists n which belongs to natural set such that 1 by n is lesser than B minus A. Okay, what does this mean? See, pick a large enough n so that 1 by n is very small. Okay, this one should be large enough so that this whole thing becomes very small. Basic mathematics, right? Then this means there exists an integer m such that m by n is greater than a. We are all doing it by Archimedean property. We can find a rational number m by n just a bit more than a. If we can do that, then m by n is lesser than b. Why do we say so? Because 1 by n is lesser than b minus a. All right. Now this proof ensures that m by n is still less than b. All right. Therefore, we have already proved it. A is lesser than m by n and m by n is lesser than b, which means R, which you have considered before, R is equal to m by n, which belongs to rational number. Therefore, which implies A is lesser than R and R is lesser than B. This was to be proved, right? So yeah, hence proved, last statement. Is this theorem clear to everybody? If not, please comment me on comment, please drop a comment and I'll just try to make it easier in the next video. Okay. Now coming to our next theorem. Do you remember the next theorem? Similar like this, just between any two real number, there exists an irrational number. This is what we need to find. We need to prove actually. Irrational number. Okay. Now what is the statement? Let A and B belong to real number such that A is less than B. Then there exists an irrational number x. We're considering this as irrational number such that A is lesser than x and x is less than B. Now what is the meaning? The meaning is you can always find a weird means non-repeating, a non-terminating number like root 2, pi, etc. between any two real numbers. All right. Now if we come to the proof, first we need to take a rational number R which belongs to the rational set, such that A is less than R and R is less than P from theorem 2. All right. Now consider x is equal to R plus root 2 by n. This is n, okay? My handwriting is terrible, I know that. Okay. Coming to our theorem, as n tends to infinity, root 2 by n tends to be 0. All right? Which implies x tends to be R. But let me clarify one point here. Why is this an irrational number? This is rational, right? But why is this irrational whole thing? Because rational plus irrational becomes irrational number. Okay. Now coming here. So x lies between a and b for large enough n. Therefore, we have proved this. Hence, this theorem is proved. Very simple theorem, all right. Now coming to our next theorem. What was our next theorem? It is the set of rational numbers is not complete. Rational numbers, set of rational numbers is not complete. This is our theorem. Now coming to the statement, there exists a non-empty subset of Q which is bounded above. But has no supremum in the rational set. Which is rational set is Q. What is the meaning of what I just wrote? Meaning is some sets of rational numbers have an upper bound. They have upper bound. But that bound is not rational. That bound is not rational. This is the meaning. If that bound is not rational, then how can it be in the rational set? Therefore, the rational set is not complete. Rational numbers is not complete. This is the meaning of the theorem. Now coming to the proof. Proof is, let's first say, let A be x which belongs to Q, the rational set, where x squared is less than 2. What can be the examples for it? It can be 1. 1 square is 1. 1.4 square is 1.96. 1.41 square is 1.9881. Okay, all belong to A. Then A is bounded above. Now let's say it is bounded above by 2. Okay, let's say this is our upper bound. Now let alpha be the supremum of A. Now we know alpha is root 2, but root 2 does not belong to rational set. Why did I say that alpha is root 2? Because just see here, x root 2, all right, least upper bound. Hence, from this, we can say, hence, supremum of A does not belong to the rational set. Therefore, it is not complete. And hence, we have proved the theorem. It is a very simple theorem, right? Now, our most simple theorem, which I've already proved in my previous video, but let's do it once more. The next theorem or the last theorem of today's class is Archimedean property. A very simple thing. We'll also do it nicely. The statement. For any two real numbers, please try to understand the statement, okay? For any two real numbers, x is greater than 0 and y. There exists a positive integer n which belongs to the natural set such that nx is greater than y. What is the meaning of it? No matter how small x is, if you multiply it with a large enough n, the product will eventually exceed any given real number y. Basically, it means no real number is infinitely larger than another. Okay? Let's take an example. Let's say x is 0.001 and y is 1000. Then if we take n as 1, 0, 0, 0, 3, 4, 5, 6 zeros. Okay? What is nx? Nx is 1000, which is equal to y. Then voila, it works. So this proves our Archimedean property. But can I just say why is it important? This theorem is a foundation for many other results. It helps prove the density of rationals. It justifies approximations in limits and calculus. It's essential for constructing real numbers from rationals. Like Archimedean property is very important. Like you have seen in most of the theorems, we have used Archimedean property, right? Now, if we just make a little summary table, right? Let's make a sweet little summary table. What did we learn from the first theorem? That natural numbers go on forever. Go on forever. From number 2, we learned there's a rational number between any two real number. And from number 3, we understood that there is an irrational number between any two real number. From number 4, we learned rational numbers miss some limits. Like they aren't complete, basically. They are not complete. And from number 5, we learned multiples of any small number, multiples of any small number eventually become large. Which is the Archimedean property. So yeah, we have completed our lecture. And that wraps up today's class on the real number theorems. We didn't just memorize. We understood what each result actually means, how it's proved, and why it matters in real analysis. These theorems are used again and again in limits, continuity, sequences, and proofs. So make sure you're confident with them, okay? And I'll upload the notes in the notes section. You can access that from the description box from my channel. That is my blog account. And don't forget to like, subscribe, and comment if you have any doubts or just for a little support or appreciation is very much acceptable. Thank you so much for watching the video and please keep studying. Take care. Bye bye.